Okay. Hey, Darina.
Hello. Sorry for the delay.
No, that's fine. Okay. Hmm. So, Yunzhen, are you ready?
Yes, I'm good.
Maybe I think we can get it started then.
Yep.
Okay, so hello everyone. So welcome to this the GA webinar series. So today it is a pleasure to have Professor Yanzhe Liao from UBC to present to us his recent research. So let me introduce the speaker a bit first. So Yanzhe is an assistant professor in the Department of ECE and also an associate member with Department of CS at at University of British Columbia. He is also a faculty member at the Weta Institute and is Canada's SIVA AI chair. So prior to coming to UBC, he was a visiting faculty researcher at Google Brain, working with Jeff Hinton and David Fleet. He received his PhD in computer science from University of Toronto. And also during his PhD, he has worked as a senior scientist, research scientist at Uber. So actually, he received his MPhil degree from Chinese University of Hong Kong, which is the school which I'm in right now. And he's broadly interested in machine learning and an intersection with computer visions and healthcare and also something related to geometric deep learning. So please join me in welcoming Yunze, and the floor is yours.
Thank you. Thank you for the nice introduction and the warm invitation. So I'm very happy to share our latest work on symmetric diffusers, learning discrete diffusion on finite symmetric groups. So this work was led by my undergrad intern, Li Zhang. He's from University of Waterloo, and he did internship with me at the Vector Institute. And then my PhD student, Dongli Yang. And this was accepted as oral presentation, and this year I clear. So first of all, let's take a look at what finite symmetric groups are. So the finite symmetric groups, we're going to use Sn to denote this group, consists of bijections from a set of n elements to itself. And the group operation is simply the function composition. So here we show a visualization of S3. So for example, for S3, you can have 3 factorial, basically 6 different bijections that map 3 elements to another arrangement of the same 3 elements. So what's the concrete example of this kind of bijection? It's shown here as a jigsaw puzzle images. For example, in the left hand side, you have 3 by 3 line pieces of image patches. So they are in a random order. But then you can have a bijection that maps this random ordering of the image patches or pieces to a well-ordered image so that you can clearly see the image content. So basically, you can represent this kind of bijection using a permutation. And that's also one of our application problems we're going to see in the later experiments. And there's also an important concept in the permutation. It's called the rising sequence, which is very crucial in understanding many of the theory behind random shuffling or permutations. So this is called the rising sequence. So the idea is to count the maximal contiguously increasing subsequence. So for example, if you have a permutation like this, which maps 1, 2, 3, 4, 5 to another ordering or ranking, which is 1, 4, 2, 5, 3. So there are two rising sequences in this example. One is the red one, 1, 2, 3. The other is the blue one, the 4, 5. So basically, you count the maximum contiguous increasing subsequences, and then there will be the rising sequence, and then the number of rising sequence in a permutation is very important to determine its property. Okay, so finite symmetric groups has many important applications. For example, as we showed, that it has been very useful for sorting. And it also has many applications in graph theory, for example, matching, traveling salesman problem, graph isomorphism testing, and also in any scenarios where order of the object matters, you can basically see this group has been used. And one more motivation is this Kelly's theorem. So this theorem is telling you that every group is isomorphic to a subgroup of a symmetric group. So basically, you can think about symmetric groups are quite universal in group theory because every other group can be isomorphically mapped to the some subgroup of the symmetric group. And if we are building a probabilistic models over symmetric groups, then we can, based on the isomorphism, we can extend it to arbitrary groups. So that's the kind of powerfulness of this symmetric group. Okay, so another important distinction between what we call rankings or orderings and the permutation. So for example, if you look at this picture, when we talk about ranking, we basically talk about ordered sequence of pieces. For example, in this case, we just shuffle the order and we have a different list or sequence of letters. But when we talk about permutation, it's essentially a function, a bijection that maps the original sequence to, or original ranking to another ranking. So this is an important distinction. Okay, so our goal of this work is to learn a distribution of probabilistic model over the finite symmetric group Sn. But this is a very challenging problem because, first of all, the size of the group is factorial, making the learning and inference computationally expensive or even intractable. And then the second problem is because it's discrete, it brings a lot of challenges in parameterized and also like gradient-based learning, because gradient-based learning favors continuous parameterization. So it's in the literature, it has been approached by many different work. For example, one of the famous work is this Plackett-Luce distribution or this Plackett-Luce model. So the idea is as follows: you first use a probabilistic model that can generate n scores to model n elements, and then given any permutation that belongs to the finite symmetric group Sn, you evaluate the probability of this given permutation by evaluating a sequence of softmax. So the idea is like as follows. So you, in the beginning, you choose one out of n items that satisfy the first permuted item or object, and then evaluate the probability using a softmax, so the exponential of this first chosen element over the exponential of all the other, including itself, all the other items. And then you leave one out, and then you evaluate the probability of the n-1 choose one scenario using the softmax again, but now because you are leaving out one item you have already chosen, so the summation only sum from the the second permuted to the last permuted items, and then so on and so forth. So basically you have a sequence of n softmax, but the number of items being considered is decreasing one by one, and in the end the softmax gives you probability 1 because you only have one item left. So that's kind of the Plackett-Luce model. And this gives you a very convenient model that have a distribution over Sn, but only parameterized by n scores. We'll see later that this distribution is quite limited, and we provide some improvement over it. So in the previous work, people have been using this probabilistic model over Sn to solve a lot of tasks. For example, people have built this Gumbel sinkhole operator and use it to do jigsaw puzzle in the in the left-hand side of the picture. So the idea is basically neuralize or parameterize the sinkhole algorithm, and then use a neural network to predict some parameters, and then run the sinkhole algorithm iteratively. And the sinkhole algorithm basically is doing row-wise rescaling and column-wise rescaling, such that you can map a square matrix to a doubly stochastic matrix, so that it's a permutation. It's in the Berkel polytope of the permutation matrices. And then another idea is to build a differentiable sorting network using some approximated differentiable approximation to replace the discrete option in some sorting algorithm. And then you can use that to sort numbers or sort images with digits. So in our model, we actually take a very different perspective. So we use a discrete diffusion to model the whole distribution over Sn. In that sense, we don't have an explicit distribution over Sn. Instead, the distribution is induced by the random process. So the idea is to decompose the challenging problem of learning a complicated distribution over Sn into learning a sequence of transition probability, which are simpler problems than directly learned distribution over Sn. And then we basically identify shuffling methods as the forward process, because the card shuffling methods have been studied for decades and proven to be useful for many applications. And it has a very beautiful theory based on the random work on finite groups. And then we propose some novel parameterization using neural network to model the reverse transition of this random process, and then learn the reverse transition probabilities, and then we provide some theoretical results about the expressiveness of the reverse process. So first of all, let's take a look at this example. So suppose we want to sort 3 4-digit numbers. Okay, so here we are given 3 4-digit numbers, but they are represented in images. For example, the first number is 1974, so it's a 4-digit number. And then the second one is 3293, it's another 4-digit number. But now we need to sort them. So this task is kind of superficial, because now you're not given the exact numbers, you are given a bunch of images. But each image has 4 numbers. And then you need to understand the image and then sort them accordingly. But this synthetic case give you a very good understanding of the setup of our problem, that you are given a bunch of objects, and then you want to sort them based on some relationship between them. Okay, so then in the beginning of the forward diffusion process, you already have all the numbers in order, and then we have basically a delta distribution, direct delta distribution on the correct ordering, which is 1, 2, 3, and then 0 probability on the other ordering, right? So the PMF is shown in the top, and then we apply the forward diffusion process, like doing one-step transition in the forward process, and then I'll explain the detail of what the exact transition probability we are using. But now let's assume we do one-step transition, so we get into another distribution. You can see that the probability mass has been redistributed, so that different ordering have some certain non-zero probabilities. And then you get kind of the shuffle the objects here, and then keep doing that. At each time, you basically have a new permutation sigma, and then you apply to the objects, and then you get different ordered objects, and then the corresponding marginal distribution has been shifted again and again. And then in the end, you hopefully to reach an equilibrium or stationary distribution where it should be uniform over all permutations. And that's the stationary distribution of the forward Markov chain. And that's basically the idea before the process. So you are given the ordered objects, and then you apply a forward Markov chain, and then you reach to the stationary, which is the uniform over all permutations. Now the question is, in the reverse, we're gonna use a neural network to learn to go from the uniform distribution all the way back to the original data distribution, conditioned on the context information. The context information in our context is simply the 3 pieces of numbers. We don't know the order, but we know there are 3 pieces of digits, and we want to figure out their correct ordering. So that's the context. Okay, so that's the overall forward and reverse processes of the diffusion model. And in the forward process, all these Q distributions are handcrafted. So we don't have anything learnable in the forward process. Instead, everything is learnable in the reverse process. We need to learn a neural network that can give us the reverse transition. So that's the overall idea. Okay, so let's take a closer look at into the forward process. So in the forward process, because Markov chain, we can write down the decomposition of the joint distribution of x1 to xt, condition x0. A little bit about notation in the diffusion literature, people denote data at time 0, and then the noisy data at time 1 to capital T. And capital T is basically the stationary noise, which is typically a uniform noise or standard normal noise. So when you see x0, it's represented data. Okay, so it decomposes into this product of conditional distribution. And then in our case, we can further decompose it into the product of the marginal probability over the permutation and another delta distribution, which represent a process that we apply this permutation to the ordered objects so that we get a new arrangement of the objects. And one important thing is in the forward process, the distribution over permutation is independent of the ordered objects. This makes sense because we are going to study methods, sampling methods using shuffling, for example, random transposition, random insertion, and the riffle shuffle, which has nothing to do with what the objects themselves are. It's just a way to create permutations. Okay, so let's take a look at random transposition. So the idea is very simple. You choose arbitrarily two or randomly two cars in this case, and then swap their position. So basically, in this case, is you choose 2 and 4 and then swap their position. So that's the random transposition. And then you can also have random insertion. So the idea is like you randomly pick up a slot in the deck of cards and then insert the top one or the ending one into that randomly pick up slot. So here we basically pick up the last card, pick up the slot in the middle and then put the last card 5 into the picked slot. So that's random insertion, which is quite intuitive. And then we have a riffle shuffle, which is a bit more complicated. So the idea is like you first split into your card randomly into 2 piles, and then the card from each pile gonna fall into the final pile randomly, but following the distribution that if there are more cards in left pile, then the probability of the card from left pile gonna fall down is higher than the right one. So basically, it's like very similar to how we actually shuffle cards in card games. We're gonna take a look at the process again. So split into 2 piles, not necessarily equal size, but then cards from 2 piles will randomly merge following some probability. And people actually create a mathematical model for this process, which is called Gilbert-Shannon-Ruiz riffle shuffle, which very accurately reflect what's going on. So if you look at the algorithm, so basically first you sample K following binomial distribution. Here N is the total number of cards. And then this K is basically the split, where the split is. So based on the sample, the value K, you split the full deck into 2 piles, right? One is on the left, which we call L, and one is on the right, which we call R. And then the L may have K cards, and then the right may have N minus K cards. And then you start the shuffling process, for example, from the left-hand side, because it has L cards, so A is L in the beginning, and then the probability A over A plus B, you have one card from left-hand side to fall down into the final pile, and the vice versa, you have B over A plus B probability to have the top card of the right-hand side, right pile fall into the final pile. So basically, you probabilistically merge the cards of 2 piles into one. And then in the end, if you have some remaining cards, you just append it. So that's the GSR Gilbert-Shannon-Ruiz model to model riffle shuffle. So we're gonna use this model to do the transition to get from a permutation to a new permutation. Okay, if you are familiar with denoising diffusion probabilistic model, DDPM style models, you will notice that in their model, you can basically direct compute the conditional distribution of xt condition x0, and record that x0 is the clean data you observe, and xt is some arbitrary intermediate state that your Markov chain has reached. And this is possible because they are using Gaussian transition probability. You can integrate and get this distribution, but for many shuffling methods, it's impossible to directly compute qxt given x0. But luckily, we can compute it for riffle shuffle. I mean, if you cannot compute it directly, what you can do is you just simulate the whole Markov chain so that you can obtain the state at time t. But for riffle shuffle, we dig into the literature, found that people actually derive it. So the distribution of the intermediate permutation, xt, given the initial one, can be described into this formula. And in this formula, here the important thing is you notice that R is the number of rising sequence determines the intermediate distribution. And then it's R again. For example, if you look at this example, you have a sequence, and then how many rising sequences are there in this example? You have two, and one is in black, the other is in red. The rising sequence capture the maximal subsequence of consecutive or contiguous orders. So this is a super important statistic that captured this property of permutations. And we can use that to directly draw samples and compute probabilities. And then we can talk about the convergence property of this forward Markov chain. First of all, people prove that for many shuffling methods we have used, like the stationary distribution is uniform. So it satisfies the diffusion model's convention that your stationary distribution is very easy to sample from. And then we can talk about how fast the forward process converge. So we're going to use the concept called mixing time. The mixing time is the time that you spend until the Markov chain is close to the stationary in total variation distance. So total variation distance in our setting is very easy to understand because it's a discrete or categorical random variable. So you just compute this difference in absolute values and then sum over all the possibilities in your support and then divide by 2. And people study the random walks on finite groups, find out that if you run the Markov chains on the symmetric groups, you will find that there's this cutoff phenomenon. So in the beginning, your total variation distance to stationary distribution kind of stays around 1 for no time until suddenly it drops to a very low value close to 0. So this is a very intriguing property. And people actually prove a symptotic bound for one, the cutoff phenomenon can happen for different shuffling methods. For example, for random transposition, the shuffling methods will have a symptotic cutoff time n log n over 2, and then random insertion is n log n, and then riffle shuffle is the best in the way that it's log n asymptotically. So which means that for riffle shuffle, the cutoff phenomenon happens much faster, which makes sense if you recall the famous results that I think Professor Percy Diakolios had proved a long time ago, that if you shuffle 52 cards using riffle shuffle, you only need 7 steps to mix it. So that's attributed to the very fast or very early cutoff time of this riffle shuffle method. And this is good for us because that means that in the forward process, you don't need many steps to reach the stationary. And actually, you can exactly compute the total variation distance when you use riffle shuffle. You can exactly compute the TVA distance between the intermediate Markov chain marginal distribution and the final uniform stationary distribution. And again, not surprisingly, this TVA distance between two distributions depends on the rising sequence R, number of rising sequence R. And then we actually simulated the process and then found that indeed there is a color phenomenon happening in the river shuffle steps, and you can see that it's between basically the step 6 to step 9 or something like that. And we can compute the total variation distance, use the formula above to validate this phenomenon. Okay, so we talk about forward process. Now let's talk about reverse process. So this is the part where deep learning kicks in and help us. So for example, condition on the context, which is a set of data or set of pieces. If you think about the jigsaw puzzle or sorting of digits applications, so you observe a set of objects, but you don't know the ordering. And then the reverse process is to run the Markov chain so that you can recover the fully ordered pieces or objects. And again, it's a Markov chain. So you decompose the joint distribution condition on context into this product of conditionals. And then because we apply the permutation to the order objects, so this distribution on the rightmost is again a delta distribution, represents the deterministic shuffling process if you have known the permutation. And then we have many choices in the reverse process. For example, we can use inverse card shuffling because we know we explore card shuffling methods in the forward process. The natural thing to do is exploit its inverse operations, and we can undo the shuffling to get the reverse process. And then we also explore the Placky-Luce distribution, and we propose the generalized Placky-Luce distribution. So for example, for the inverse card shuffling, the simplest to do is like take the inverse process, for example, transposition, because in the transposition, random transposition, you random pick 2 and then swap. And then the inverse of this is again a transposition that you use a neural network to parameterize where you pick up the 2 and then swap again. So that's the inverse transposition. Very intuitive, and then inverse insertion is also very intuitive because in the forward process, you random pick a slot and then put the top card or ending card into that slot. Now, in the inverse process, you basically random pick a card and then put it in the top or put it in the end. So that's the inverse process. And then for the riffle shuffle, the inverse process is a bit different, but still it's intuitive in the way that because when you merge 2 pairs of cards, you basically make a random battery choice by say, okay, I'm gonna pick the top card from the left, then I put left first. I'm gonna pick a top card from the right first, and then I'm gonna put the right one first. So basically, every step you are making a battery decision, choosing left or right. And then in the inverse process, it's basically the same idea that for every card, you need to do a batterized decision that you either merge into the you either choose the left pair, put it in the left, or choose the right pair, put it in the right. So basically, you go from order sequence and split into two pairs. So then you just model this process using a sequence of, for example, sigmoid distribution. Okay, but then we also try other alternatives like Placky-Luce distribution, because this is what people in the literature have heavily used. So we can use a neural network to predict n scores and then use this Placky-Luce distribution to give us a valid distribution over Sn. But the problem we found with Placky-Luce distribution is it's regarding its limited expressiveness. For example, we first show that it cannot represent the delta distribution, which is actually quite useful in the shuffling method because some steps are exactly delta distribution. So the idea is like if you want to use the Placky-Luce distribution, the PL distribution represents delta distribution. So what happens is every single product term in this distribution needs to be 1. So basically the softmax has to be 1 for n such softmax. And this is impossible because if you make the first softmax to output 1, then you need to force the scores of all the other permuted items to have relative infinity scores in order to make the first product term to be 1. And if you force that to happen, then the other product terms cannot be 1. So there is a contradiction. Then you can't force this PL distribution to be exactly delta. And then what's the way to remedy this issue? So we found that, okay, a simple way to do it is instead of predict n score, you can predict n square score. And each row, you have n score that you just model one conditional distribution in the bracket loose distribution. So the idea is still you do n choose one, and then n minus one choose one, and then minus two choose one. You do a n step sampling, but now you have different scores at each step, so that you have n squared score, and they are free to model whatever distribution in the middle. So then, if you compare the two expression, because it's the same kind of process, so you have almost the same expression, but now the only difference being for the first n choose one, you have n scores, which is indicated by the red index one. And then in the second step, you do n minus one choose one, so you have S2, and then so on and so forth. So you decouple the scores you use at different steps. And this is very important because if you do so, you can prove that the GPL, the generalized bracket loose distribution, is more expressive than the PL distribution. So in particular, we show that any data distribution over permutations can be modeled by the GPL parameterized reverse process. So we can quickly go over the results by give you the intuitive proof of the results. So first, let's look at the first lemma. So this lemma is say, okay, the GPL distribution can represent the delta distribution, which is the case because now we can freely set the score so that in the first step we have a delta, in the second step we have a delta, and then we have n delta multiplied together. And then the second lemma we prove is like given two permutations, they only differ in the swap of the last two indices. For example, in this case, you have a permutation sigma, you have permutation pi. The only difference lies in the last two indices, because this one is n minus one mapped to sigma n minus one, and then n maps to sigma n, but the other one is like n minus one mapped to sigma n, and n mapped to sigma n minus one. So they only differ by two. And then we prove in this lemma, say that GPL can represent any distribution whose support is a subset of these two permutations. So basically, if you have two permutations, they only differ by two, then the GPL can model any distribution whose support is a subset. And we're going to use these two lemmas and use inductive proof by induction to prove the final result. So here, instead of give you the full lengthy proof, I give you a concrete example to showcase the idea of the proof. So in order to show that the GPL can model any data distribution of permutations, so we basically repeatedly using the previous two lemmas to reallocate the probability mass so that going from a uniform distribution, you can reach any data distribution. So here, we show you a concrete example in S3, which have 6 permutations. And then we color them differently in a way that for two permutations with the same color, for example, these two, they only differ by the last two indices, right? Because here 2 maps to 2, 3 maps to 3, but here 2 maps 3, 3 maps 2. And same idea for the blue ones and the red ones. So we basically group them into a bunch of pairs, and within each pair, they only differ by last two indices. Okay, so that's the first step, and that can be done for any kind of finite symmetric groups. And then we start with the uniform distribution because here is S3, so the uniform distribution is 1/6, and then the target distribution, arbitrary target distribution, is shown in the above. Then what we first do is we first allocate all the probability mass into one permutation. This is doable because of the lemma 1, because we proved that you can use a delta distribution. You can use GPL to represent the delta distribution, and with the delta distribution as your conditional transition probability, you can move 1/6 to this position, 1/6 to this position, and so on and so forth. So basically, you can use lemma 1 to finish this step, and then we can reallocate the probability mass 1 into 2 parts because the target has 1/4 on this permutation. And then we can split into 2. Why this split is possible is based on lemma 2, because for lemma 2, we know that if you have 2 permutations, they only differ by the last 2 indices. We can use GPL to represent any transitional probability, so then we can allocate the probability 2. So now we satisfy the first probability, probability of the first permutation. And then we keep doing, we move this 1/4 into this position, because in this position you have 1/4 in the target distribution. But how can you move from the first to fourth? This is again by lemma 1, because the conditional distribution of the transition from this distribution to this distribution is a delta distribution. And you can use lemma 1 to prove that this is doable. And then again, you can do the split. And now you reach the target. And this why this split is possible is because lemma 2, because for lemma 2, we show that if two permutations only differ by last two indices, we can model any transition probability that finish the split. So the idea basically is like you use an inductive proof to prove that you grouped all permutations into a bunch of pairs that like each pair they only differ by 2, and then you can repeatedly use lemma 1 and lemma 2 to shift the probability mass, so that in the end you can model any data distribution. Okay. We'll not go into too much details of the rigorous proof, but to give you this example. Okay, so that's the reverse process. So we identify a lot of options. Now, how can we train the diffusion model? And we're gonna resort to this evidence lower bound. So the idea is like you rewrite this log likelihood using a lower bound instead of the original one, because the original log likelihood is intractable. And in this lower bound, you can find out that you first gonna sample from the forward distribution for the process, because in the expectation you cannot exactly compute, so you're gonna resort to Monte Carlo sampling. You're gonna sample from the forward process, and then you're gonna evaluate the log ratios in the bracket, and also this probability. But this probability is regarding the X capital T with the uniform distribution, so you actually don't need to worry about it. The only thing you need to learn is by maximizing this log ratio in the objective. So this is a little bit different from the traditional diffusion model, again, because of the fact that, I mean, traditional diffusion models start with elbow as well, but they use the Gaussian transition probability so that you can easily get QXT given X is 0. So then you can rewrite this objective by using the what they call the Black-Rao realization, Rao-Black realization to kind of rewrite it to reduce the variance. But here we can't do that because, again, for Manning shuffling method, we have no analytical form for this distribution, and also the KL divergence in our case is intractable because it's not Gaussian, has no analytical form. But we can still sample and maximize elbow. And for our modeling choice, we basically use a transformer, and it's not very surprising because transformer performs super well for sequence modeling tasks, and given the input sequence of n items, where each of them might have d-dimensional feature, you use a numerator to directly model the reverse transition probability. And this is not something very local, I would say, just using the transformer in our case. But the output of transformer is the parameters of the GPL distribution. Okay, so for PL and the GPL, we can actually merge some reverse steps so that the reverse sampling is more memory efficient and faster. So how does that work? So the idea is as follows. Suppose in the forward process, you run 15 steps, right? And then in the reverse process, the way you can do it is you can also do 15 steps so that you go from stationary to the data distribution. But you may say, okay, 15 is too much. Can we skip some of the step in the reverse process and then try to speed up sampling? And it's possible for PL and GPL because PL and GPL has a very large support in on the finite symmetric groups. And this is very important because if you look at this ratio, so in computing this ratio in the objective, if we sample from Q distribution, the forward process, and the support of the Q, if it's larger than P, then we're gonna have a trouble because that means we're gonna sample a permutation that goes outside of the support of the reverse transition probability. Then we're gonna have probability 0 here because it goes out of the support of this p theta. Then you have log 0, which gives you electric infinity. You run into a programming optimization. So that means in traditional card shuffling and inverse card shuffling method, you need to be very careful about, for each transition step, how the support size changes. So, but the lucky thing is for PL and GPL distribution, you don't need to worry too much because the PL and GPL can model many different, or for GPL, we prove we can model all possible transitions. So the support is the full SN. So then you don't need to worry about log 0 stuff in computing distribution. So that's why you can merge some step, because you can reach from one state to basically any other state in the SN. Then in the distribution of SN, then you can merge some of the steps so that you can reduce the Markov chain length in the reverse process. But then the question is how to design a merge process. So we basically, based on this TV distance, the cutoff phenomenon that we compute per step TV distance. You can see that in the beginning, the per step TV distance is as high as 1, and then suddenly it drops very low and then almost goes to 0 in the last. So then we try to merge some steps in the beginning before the drop, before the cutoff. And then for the cutoff, we have 1 or 2 steps. And then after the cutoff, we have maybe 1 or a few steps. So that's the intuition. Okay, so after you parameterize the reverse process, in the end, for many applications, you don't care, you don't directly care about distribution, you care about actual sample from the distribution. So then you need to have some decoding methods. So here we don't do anything surprising. So we just follow what people use in large language models, right? You have a distribution over sequences, and then you need to decode the actual samples. You can use greedy decoding, which takes the argmax of the individual conditional distribution, and then you get a sample. And then you can also do beam search. So basically maintain a dynamic buffer of K candidates and then try to find the most probable K sequences. Okay, let's take a look at the experiments. So we evaluate the experiments using 3 different metrics. First is the Kendall-Tau coefficient, which measures the correlation between rankings. So if you have 2 different rankings, and then if this coefficient is high, then it means that 2 rankings are highly correlated. It's like the Pearson correlation, but it's computed for rankings. And then you have for accuracy, because for problems like jigsaw puzzle and the sorting, you can have accuracy computed based on the final results. And then you can also have a correctness. So this is to say that if you sort everything perfectly, then it's a correct prediction, and then you count +1, and then you divide it by total number of problems. So correctness is a more strict or more challenging metric than accuracy. Accuracy is per pieces or per object, but correctness is per sequence. You can think about that this way. Okay, so we first sort 4-digit M-list images. So you're given a bunch of images. They are in random ordering, and then the model needs to learn the reverse process. You store them in a ascending order, for example. So this is a visualization of what's going on. And then we compare with a bunch of methods which use differentiable sorting, which use error-free differentiable sorting, so on and so forth. And then the interesting thing is, like, as you increase the problem difficulty by increasing the sequence length, you will find that in the beginning, our method is comparable or maybe slightly worse than still there are methods. But then when you go from really challenging cases where the length of the sequence goes to 52, 100, and 200, our method is way better than the other, because you can see from other state-of-the-art methods, the accuracy drops to exactly 0 because they cannot sort even a single kind of digit right in that case. And then we do jigsaw puzzle problem where the input is a bunch of randomly chopped image patches, and then you want to recover their correct arrangement. And we do this experiment in the 3x3 setting and then 4x4 setting. And then we compare again with a bunch of methods like gumball simple, deep sort, and so on and so forth. And you can see that on the noisy M-list and CFR10, no matter it's 2 by 2, 3 by 3, 4 by 4, or 6 by 6, you can see that our method outperforms state-of-the-art methods significantly. And then the last problem we try is this TSP problem. So the idea is as follows. In the TSP problem, we were trying to find a tool so that you can minimize the total weights or total lengths in some cases, right? So here, for example, denote the vertices V1 to Vn in the 2D plane. And then we can rephrase this problem by finding a permutation sigma such that we can minimize the tool length. So different permutation can exactly represent different tool because you only visit one position once in the permutation in that case. So basically, you want to find the permutation such that this sum is minimized. And then we use the discrete diffusion model to model this problem. And then we compare again with a bunch of learning-based methods and also traditional OR solvers. And you can see that our methods outperforms the learning-based methods and is approaching the OR solvers because the OR solver is the ground truth one because it solves the problem using enumeration or exhaustive search. And our methods learn to solve it. And this is the results on TSP 20 and TSP 50, and the number means the number of vertices in the problem set. Okay, so that's pretty much of everything of my talk. Thank you for listening.
Okay, thank you, Renze, for the nice talk. So, is there any question from the audience? So feel free to unmute if you have any questions for Renze. So maybe I have one first. So I'm still a bit confused about the first numerical examples. So where you try to actually like sort the handwritten digits, like the M-list ones. So like how does the accuracy thing compare to, let's say you directly detect the 4 digits and then you sort it? Like I'm not sure whether I get what's the main insights here.
Yeah, so here you are given a bunch of images basically.
Yeah,
right?
okay.
Each image is containing 4 digits.
Yeah.
Then they have a numerical value, right? So we want to sort based on that numerical value. For example, this 2,960 is larger than 1,270. Then you should put this guy first compared to this guy. So that's the task. And then in this task, you need to have basically an encoder of a neural network that can recognize digits from the image, which is simple, right? But the challenging thing is like when you recognize the digits, can you sort them correctly?
Okay.
That's the part where the discrete diffusion kicks in.
Okay. So you mean the sorting is the sorting thing is going a bit beyond simply like ascending order. So there's no fixed rules before like there's like a non-standard rule so that you didn't know beforehand.
Yeah, because all these numbers are randomly generated during training and testing.
Oh,
You can't just memorize them.
I see. So I got it. Okay. So uh hmm,
I have one question.
Sure.
yeah.
So you say you are liking this method can solve the puzzle, but actually the real puzzle is like it's also an ordering problem, but it's like every piece is not only a square, they also have some convex and concave
Different
part.
shape.
Yeah. But it's also a order problem. So
Yes.
so I'm thinking if it's possible, so because it's still an ordering problem, but I don't see a possibility this one can be extended to the general puzzle.
Right, that's a good question. So I think you need to define some energy function that measure different configuration with different shapes. It's not because in our case, for example, we can directly, if our model predict the ordering, right? We can order the patches and then we get the images, and then we can compute the mean square error between the shuffled image and the ground truth image to measure how good it is, right? And then in your case, because the shape may be complicated, so that some ordering may give you invalid assembly, right? If it's invalid, then you might need to design a new energy function or penalty so that you can give them some penalty. Otherwise, you can't directly compute mean square error as what we do in our case, because we are like split the images into regular patches. We can directly use MSE. Yeah. So you need additional design to measure the configuration, like invalid configuration, for example.
Yeah, and also for some puzzles, in your case, actually all the pieces are different, but actually we can have some pieces are the same. You know what I mean? Like piece one
Yes.
and piece two very the same. How can you
Yes.
distinguish them?
Yeah, that's a good question. That's why you see in our experiments, we call it noisy MNIST, because in MNIST, the background is all black. If you really allow two identical patches to happen, then the model will have confusion in the way that, I mean, each like different ordering may give you the same result, right? So then the model there may be a uniform distribution over the all correct solutions. But in our experiments, we intentionally avoid such a situation because that's not fair for all the other methods. Because when they do that, they also make sure that each patch is unique. So they add some Gaussian noise to the MNIST images so that even in the background, you don't have identical patches.
Oh, okay.
Yeah.
Thank you.
So does it mean that actually even in practice, it might be better to add noise anyway to the jigsaw puzzles?
Yeah, it could be like you can do the symmetry breaking procedure
Yeah,
to break that. Otherwise, you might have confusion in the learning process.
makes sense. Okay. Um, So I have maybe one more questions. So you mentioned about that you mentioned that when optimizing the elbow, so you cannot use the Gaussian models because it's not a Gaussian distribution. So then you said that you sample it and optimize it. Does it mean that you're doing sample average approximation here?
Sorry, say again. What's your last part
So
of
is
that?
it like that you do sample average approximation? So you replace
Yeah,
replacing the expectation by empirical sum.
yeah. Basically, we sample from the forward process, and then we we sample in the batch mode so that you have many sequence from the forward process, and then you do the Monte Carlo estimation by computing the ratio here. Yeah,
So
that's
isn't
the
that
yeah.
actually quite heavy?
Yeah, it's slower than the traditional diffusion model for images because you can first sample an arbitrary t and then directly sample xt from xt given x0. But
Mm.
again, for the riffle shuffle method, this
Uh-huh.
is possible because you can random sample t and then sample xt given x0 because for riffle shuffle you have the analytical distribution. We show I think.
Oh,
Somewhere. Let me try to search it quickly. But
maybe
yeah,
maybe
here.
reverse process, right?
Yeah, for riffle shuffle it's possible, but for other shuffling methods, this is impossible. So that's why
I
we
see.
provided two kind of recipe. Like for general shuffling method, you have to go through a slow sampling process, simulate the full Markov chain. But for riffle shuffle, you can use this distribution directly shuffle LET.
I see. So So do we have further question for Yanze? So if not, please join me to thank Yanze again. So thanks for waking up very early. And
Yeah, thank you.
okay.
Thank you very much.
Magic.